Hello everybody, welcome back. Today we're going to find the eigenfunctions and energy eigenvalues for the particle in a spherical box problem with r is less than a. So the Schrodinger equation describes the complex wave function for a particle, and since we're dealing with a spherical box, we know that it's going to be a function of r, theta, phi, and t. And because it's trapped in the spherical box, we know that our v is going to equal 0 everywhere. And at the boundary of the box, which is a, um, the wave function is going to equal 0. So that means that at a, theta, phi, t, it's also equal to 0. Okay, so since we know we're working with spherical coordinates, I'm going to go ahead and expand the Laplacian in spherical coordinates. I'm also going to substitute the v equals 0, but this part of the givens we're not going to be able to use for quite a bit. So let's go ahead and do that. We're keeping the multiple out in front. This is the reduced Planck's constant. The capital M is the mass of the particle. And this is what the expansion of the Laplacian is in spherical coordinates. It's r squared dr. Then this is 1 over r squared sine theta d theta sine square, or sine of theta d theta. And then the last term is 1 over r squared, r squared sine squared theta d squared psi d phi squared. And this is equal to the other side of the equation. I is the square root of -1. H bar is reduced Planck's constant. D psi dt. Okay, so in order to solve this, we are going to assume that our psi is equal to some function of r alone times some function of theta alone times some function of psi alone, or phi, sorry, times some function of t alone. And so the actual solution is more complicated than this, but this will give us the functions that we can then use to build up whatever else we need. So with this being the case, if we were to take the derivative of psi with respect to r, for example, like we have to do right here, the rest of it is just going to be a constant multiple. So that means that they're not affected by that derivative at all, or any other derivatives with respect to that function. You can see that the same thing happens here. We have a partial derivative with respect to theta, and another partial derivative with respect to theta, and then 2 with respect to phi, and then 1 with respect to t. So for all of these terms, they are not the other parts of the equation, the other parts of psi do not affect it. So they just come out as constant multiples. So we'll just go ahead and divide by all this. So instead of just having, theta, psi, t for this one, and, the other was for all that, we'll just have 1 over r. So let's go ahead and do that now. So it's going to be same thing out front, 2m. So this is going to be 1 over r d dr. Sorry, we can't forget the other term out front too. D dr are actually these are not partial derivatives anymore. They're full derivatives. So because we're only doing it to a function of r alone. So then this is 1 over capital theta, 1 over r squared sine theta, d theta sine theta, d capital theta, d theta. And then this last term, well, not last term, but the last term on this side is 1 over capital phi, 1 over r squared sine squared theta d capital phi, or d squared capital phi d lowercase phi squared. And this is equal to 1, actually 1 over t I h bar dt dt. Okay, so an interesting thing happens here. We only have t and functions of t on this side of the equation. There are not any t's anywhere on this side of the equation. And this is identity. This isn't something where we need to find a value of t where this is equal. This is equal all the time, and we know this. So if the t's are only on this side of the equation and the functions of t are only on this side of the equation, then that means that this side of the equation doesn't depend on t at all. So what this actually equals to also can't, because this is, this is equal to this, and this doesn't depend on t, so this can't actually depend on t either, really. Well, when it's set up like this, so what this ends up meaning is that this has to equal a constant, because that's the only thing that it can equal without depending on t. So, and this is actually a very special constant. This is the energy. So I'm going to rewrite this dt dt. This is equal to, and we're going to call it E. So this is the technique of separation of variables. So we're separating the t's out, and we realize that it can't actually equal something that depends on t. So so this means that we can rewrite this as dt equals E over I h bar, and this is times t. So there's only one function that's equal to its own derivative times a multiple. This one is not a super difficult one to figure out. So this one, so t, which is our function of t, remember, t is equal to, and also this over I. You can bring the I up to the top of the fraction if you put a negative out in front, which is what I'm going to do. So t is equal to negative E I over h bar t. So we have our first variable taken care of. So this is a very similar process to what we're going to be doing for all the rest of these, but it does get a little more complicated as we go on. But we know that this is true, so we can put it back into the other side of the equation. I don't really want to write it all out again, but so actually, yeah, I'll just go ahead and write it out again anyway. This requires a lot of actually, what I'm gonna do to save myself a step, I'm gonna see there's a factor of 1 over r squared in each part of this. So I'm gonna multiply that over to the other side. I'm also gonna multiply this constant multiple over to the other side too. So we won't have to rewrite it quite as many times then. But this problem does require a lot of writing. Um, so this is just rewriting the same thing. Capital thetas look kind of weird. I don't know if I'm just drawing them weirdly or if there's a different way to do it. Um, but it's also the easiest way to get confused. I mean, the other ones, it's kind of obvious whether you're doing capital or lowercase. So I do kind of have to draw them kind of wide so that you can see the separation from the middle line. Otherwise, we'd just be doing d theta, and it's like, isn't that equal to 1? And it's like, no, it's not, because we're dealing with a function and its argument. So finishing up rewriting this, sine squared theta d squared capital phi lowercase phi squared. And like I said, we know that this is equal to e, so we can keep the e on this side of the equation. And when we multiply over all that stuff, we end up with, we end up with negative 2m r squared e over reduced Planck's constant squared. Just making sure I got this right. Yep. Don't want to make a mistake in the middle of this problem. So what we can do now is so this actually is a function of r, because you see, because it has the r squared there. So even though we spent this time to write it to the other side of the equation, I'm gonna I'm gonna go ahead and rewrite this again and move this back to the other side of the equation again, so that we can do something else. And also, notice how there's a sine theta here and a sine squared theta here. We want this by itself as phi, phi, d phi, all that stuff, without any other variables in there. So we're going to multiply through, we're going to subtract this on the other side of the equation, and we're going to multiply through by sine squared theta. It's going to add a theta term here and not really do anything good for us here. But that'll allow us to have phi by itself, and then we can separate that out. All this to say, we're rewriting this again. So I'm going to put a parenthesis here just to kind of keep the different terms separated. dr r squared dr dr. You should make that a little more clear. It's not an a. We do have an a in this problem that is related to r, but that is not it. So bring this over to m r squared h bar squared e. And then we actually have to multiply by sine squared theta. And then for the theta part, we have 1 over capital theta times sine theta d theta sine theta d theta d theta. But this finally gives us 1 over phi d squared phi d phi squared. And this is equal to 0 since the only thing that was on this side of the equation we moved back. Okay, so now we can separate this off. We can separate the phi part because phi is only in this part of the equation and nothing else has any phi's. So that means that this whole section cannot depend on phi. There's no way it can because there's no phi's here. So this must equal some sort of constant so that this can also equal that same constant. We're separating the variables again. So that means that we know that 1 over phi d phi squared, or d squared phi d phi squared is equal to some constant, and we're going to call it negative m squared. Why are we calling it negative m squared? The solution to this problem, to this equation, is equal to e to the plus or minus I m phi. And you remember, we're dealing not with just with ordinary coordinates, we're dealing with spherical coordinates, meaning that phi has to be a periodic function, and the period has to be 2 pi. Because if it wasn't that way, then depending on how we looked at a point, it would have different values, and that is unacceptable. Every value, no matter no matter how we look at a point, it needs to have the same value. So this is the way that this equation has periodic functions or periodic solutions with a period of 2 pi. If we did any other, if we did positive, it would be exponential. If we didn't do it squared, then we'd have other problems, all that kind of stuff. So this is what we're going to use for that. Actually, what I'm going to do is I'm going to write the parts that we have down here in blue so we don't forget them, and so that we can look back at them later. So t is equal to e to the negative e I over h bar. That's an ugly h bar t, and phi is equal to e to the plus or minus I m phi. So yeah. Also, m has to be an integer. So now that we have this, we can substitute this back into our equation up here. But instead of substituting it into this one, I'm not going to substitute it into that one. I'm going to substitute it into this one. Well, kind of. This is still going to be on the other side of the equation. Actually, I'll just go ahead and rewrite it. You guys don't need me to explain. Okay. So this is going to be 1 over r dr, or d dr, r squared dr dr. This is going to be plus 2m r squared h bar squared times e. And then we're going to put this sign squared back to wherever it needs to go. So then we're going to have 1 over capital theta. 1 over sine theta. d theta. Sine theta. D theta. This is a capital theta. D theta. D theta. And then we know that this is now our constant negative m squared. And also it is over sine theta, sine squared theta. So this is going to be negative m squared sine squared theta. Yeah, equals to 0. So now, if you notice, this part of the equation here has all of the thetas, and this part of the equation has all of the r's. So we're finally down to a function that has 2 variables, meaning that we can separate both of them in this step rather than separating a part of it and then figuring out what to do there. We can finally separate both of the equations here. So I'll just rewrite the r part first. 1 over r d dr r squared dr dr plus 2m r squared h bar squared e. This equals some constant k. And then on the other side of things, we have 1 over capital theta. Actually, I'm going to go ahead and, well, yeah, never mind. I'll do that step in a little bit. Sine theta d theta sine theta d theta d theta minus m squared sine squared theta equals, and this is going to equal negative k, because if this is equal to positive k, then this has to equal to negative k, because they have to equal all that stuff. So, yeah. Let's go ahead and rewrite this equation this time. So I'm going to rewrite the theta part. So I'm going to bring k over to this side of the equation, and then I'm going to multiply through by capital theta. And you'll see why we're doing that in just a little bit. This is going to be sine theta d theta sine theta d capital theta d theta. And then this is going to be plus k minus m squared sine squared theta times capital theta equals to 0. And you may be wondering why we did that. That doesn't really look any better. But I'll let you in on a little secret. We already know how to solve this. If you remember in chapter 12 when we learned about the associated Legendre equation, this is the differential equation that gives us the associated Legendre polynomials. And if you look at this, it looks pretty similar to what we have here. In fact, if you do the substitution x equals cosine of theta, what you end up with is exactly this, except for one thing. K needs to equal L plus times L plus 1. In order for this to be finite, L needs to be an integer for this. So L times L plus 1. We have a restriction on what k has to be for our function to actually mean something to us. So this means that this all turns into theta is equal to, let me make sure that I don't mess this up. Theta is equal to P of M L cosine theta. And I'll write this down over here too. Yeah, I'll write it down over here. Capital theta is equal to P M L cosine of theta, and L has to be an integer. So we decided that k was equal to L plus, or L times L plus 1. So we're actually going to use that and put this back into the R equation, which we have here, because we have a k here, so we're just going to substitute that in, since we already have a restriction on L. So that'll work out. So 1 over R, actually, yeah, I'm not going to skip a step here. Actually, I am gonna skip a step here. I lied to you guys. Let's see. Yeah, okay. So dr r squared dr, and that's equal to so this, yeah, okay, so this is equal to 2m r squared over h bar e, I'm going to put parentheses here, minus L times L plus 1 and this is all multiplied by r, and this is equal to 0. Okay, so now if you actually, what I'm going to go ahead and is I'm going to go ahead and do this part explicitly. So when you have this dr, the ddr, r squared, dr, dr, all you have to do is do the product rule for that. So let's do the derivative of this one first. That's just r squared d squared r dr squared, and that is plus 2r dr dr. Because when you take the derivative of that. So what I'm going to do is I'm going to get rid of this part of it. I'm not going to rewrite this all again just for this part of it. I'm going to erase this, and I'm going to rewrite that part in here. And you can see why I'm doing that in just a little bit. I'll explain. So this is going to be r squared d squared r d r squared plus 2r d r dr. Okay. Now, does this look like anything that we've seen before? Actually, it does. So what I'm going to do now is there's a lot of r's in here. So what I'm going to do is I'm going to take off an r squared from each term. And you might see where this is going if you've looked at the other functions that we have waiting in our red section of stuff we know. So this is going to be 2 over r. That r squared is fine, it's gone. And this is going to be over r squared. So what does this now look like? This now looks like the generalized Bessel equation. Instead of y, we have r. Instead of x, we have the other r. So we just need to find what constants fit for this, especially since we have this term here, and then we have a over r squared term there. Yeah. So what we're going to do is we're going to find out what functions fit for this. So, or what constants fit. So we'll start with a. What is our a term equal to? So a is going to be equal to, let's see, we have a 2 over r, and this is a 1 minus 2a. So that means a has to equal negative 1/2. So we have that. Now I'm going to go a little weird. We're going to find out what c is next. Notice that for this term here, that does not have any r's in it. So that means that this exponent must be equal to 0, which means that c has to equal 1. So c is equal to 1. And then what does b equal to? B is equal to, since we know that c is 1 and then this term goes to 1, b is equal to whatever we have here but the square root of it. So b is equal to the square root of 2m e over h bar squared. Kind of a messy one, but it's fine. It'll work out. And then finally, to find out what p is, that's a little more difficult. So I'm going to rewrite this in terms of like what we have here. So that's going to be, so that means that a squared minus p squared c is equal to l plus 1. Okay, so rewriting that again, that's going to be 1/4 minus p squared is equal to l squared plus l. Further, p squared is going to be, let's see, the 1/4 goes over there, and then everything gets, actually, oh yeah, I was like, well, this isn't working. That's because that negative is very important. You can't forget it. So this is negative. This is negative. And then this is also negative. Sorry about that. So that means that p, you put the 1/4 over there, becomes a negative 1/4. You cancel all the negatives. So p squared is going to be equal to L squared plus L plus 1/4. And if you know your factoring, you know that that means p is equal to L plus 1/2. P is equal to L plus 1/2. So that means that the solution to this function, r, is equal to x to the, or nope, r to the negative 1/2, z, p is L plus 1/2. Remember that L has to be an integer, so this always has a 0.5 at the end of its decimal. And then b is equal to that thing, to m e h bar squared, and then x to the c. C is 1. This is not c, x, this is r. Okay, so just as a little bit of notation, remember that z of, z whatever of something is a linear combination of whatever solutions of Bessel's equation that you want. So that means that you have your j of n and you have your y of n. Any linear combination of that is what z of n is equal to. So that means that we can multiply this by anything and it's still a solution. So what I'm going to do is I'm going to multiply it by square root of pi over 2. And if you can see why we're doing that, that's because that turns it into the spherical Bessel function. And also, all of these are multiplied by arbitrary constants anyway, so it doesn't really matter. So that means that this r is actually equal to it's equal to one of the spherical Bessel functions of b times me h squared of r, or it's equal to some combination of this y of n thing. me to, I'm really tired of writing this out by now. Okay, r. However, if you know something about your spherical Bessel functions, you know that this y of n is equal to infinite or negative infinity at at r equals 0, or at its argument equals 0. Unfortunately, r equals 0 is part of the spherical box that we're dealing with, and we cannot have negative infinite whatever we're dealing with. So that means that this y of n is no longer a candidate for this function. So that means that our r is equal to j of n square root of 2 me over h bar squared r. Okay, so we have all 4 parts of our function. Remember that we decided up there that this is how we're going to treat this function. So we have all 4 parts of our function. I'm actually going to move the screen down a little bit so that we actually have some more room. All the important stuff is still on the screen right now. So this means that, okay, so we have 1 or 2 more steps that we have to do. Notice how we have not used this. This is why I kept it on the screen. We have not used this yet. This necessary condition that at r, or that at a, our function is equal to 0. We have not used this yet, so we're going to use it now. We're going to use it as far as this is concerned. So that means that when we substitute a into r, which means that that's the spherical Bessel function of n square root of 2me over h squared, and this turns into an a. So this has to equal 0. So there's not really an easier way to do this than to just say that, well, that it's a 0. So the only variable we have in here really is E. That's the only, everything else is like given to you in the problem basically. The M would be whatever the actual mass is. The E is really what we're interested in finding. So what we can tell from this is that um, we're going to solve, well, actually, here's what we're going to do. We're going to say that we're going to put everything under the square root. 2m e a squared over h. This is still under the square root. This is a 0 of, actually, I should have mentioned this earlier. This is not an n. This is an L because, whoops, because of how we, because yeah, this is an L there, so this is really an L. That's really an L. This is really an L. Sorry about that. This is a 0 of JL. So what that means is we can turn this on its head and say that E is equal to, so I mean is an equal sign basically. So we're going to square this side and then take out everything that isn't the E from this side and move it over to the other side. So E is equal to h bar squared over 2m a squared times any any ji or jl 0 squared. So this is actually one of the main results of what we wanted. We wanted to find the energy eigenvalues. These are the energy eigenvalues. This is why in quantum mechanics, a particle can only have a set amount, discrete amounts of energy. It's because of this, because of all the stuff that we've done and the qualification that the wave function is 0 at the boundary. It means that E can only take on these values where you have a 0 of JL. Now, to be fair, there are like infinitely many of these. There's actually like doubly infinitely many of these because not only are there infinite zeros, there's also infinite L's that you can plug in for the function. But it's not continuous, it's discrete, and that's what's important. So now that we have this, we used all of our information that we have. So all we need to do is write it all up together. So I suppose I'll write this in blue. Our wave function is equal to, and keep in mind, it's not equal to this. It's equal to an infinite sum of these. It's an infinite series of these. But it's still, this is what the eigenvectors are for this equation. JL 2m e over h bar squared. This is the h bar is still under the square root. R. Let's see, what next part did we have? We had the theta part next. So that's P M L cosine. The cosine is the argument of theta. And then the next part is the phi part. E to the plus or minus I m phi times the t part, which is E negative E I h bar t. And remember, m has to be an integer, L has to be an integer, and E has to be r squared 2m a squared times any JL 0 squared. Okay, this was a long problem. Thanks for sticking with it. I hope you enjoyed. This is the last video in this series. Thank you for all your support. Subscribe to the channel if you're interested. I have some cool stuff in the pipeline for this channel, and I hope you'll stick around and watch that too. If not, watch the rest of the series, and thank you so much for watching.